Thank you. I think it's appropriate for this meeting to quote Blaise Pascal, who was saying, I say it in French, je tiens pour impossible de connaître le parti en tant que parti sans connaître le tout, mais je tiens pour non moins impossible la possibilité de connaître le tout sans singulièrement connaître les parties. The physicist and Nobel laureate Jean Perrin first demonstrated experimentally in 1908 that atoms existed. For him, science was a way to replace the complexity of what is seen by the simplicity of the invisible, unquote. As any child, any student apprehends the world while perceiving it by the senses, an education aimed at understanding and eventually mastering science is exactly confronted to this step, namely to jump from the visible to the invisible. One has to move from the real object to the mental object, from the concrete to the abstract, from the obvious to the counterintuitive. Even if today we can show pictures of atoms in crystals or proteins to our students, the invisible is still there, hidden in the quarks, the dark matter, the equations, and the symbols. Science education is difficult because we can say with Bachelard that, I quote, there is no such thing as the simple, we just know the simplified. And science education becomes more difficult as the complexity of science immensely increases. Traditional science education aims at training specialists, focusing on excellence in one discipline, such as physics, with little or no exposure to epistemology or philosophy. But today, the complexity of modern physics or biology and the ethical issues met by the applications of physics or biology question this traditional approach. Second, traditional education pays more attention to technical ability or learning facts than to the understanding of what is a scientific process. But today, the importance of understanding science and technology in the life of every citizen also questions this traditional attitude. In front of what I call inadaptations, deep changes may be necessary. So, in the first section, with a few examples, I will give some signs detailing why these changes are needed. In the second one, I examine possible evolutions for an advanced science education with some examples in physics, my own field. In the third, I discuss how the goal of a science for all reintroduces the person in the objective realm of natural sciences and forces to abandon over-specialized subjects for an interdisciplinary vision of education. I will focus essentially on primary and secondary education, but many observations may also apply to tertiary education. So let's first discuss a new vision of sharing science. Traditionally, science education aims at preparing a small number of specialists, mastering a well-defined field of knowledge. Because of the ever-growing complexity and abstraction of the concepts, a hyper-specialization of individuals is practiced and keeps increasing. Related to this complexity, modern and central concepts in physics, such as special or general relativity or quantum mechanics, are so distant from familiar representations of nature that secondary education often ignores them, transmitting a physics apparently simpler but older than a century and disconnected from today's applications. In addition, physics education observes a strict, although recent, 20th century maybe, separation between the objectivity of natural sciences and the various facets of subjectivity explored by the humanities. As a consequence, in our secondary or post-secondary lectures when training physicists, the historical emergence of scientific concepts, the epistemological difficulties, the interfaces with other fields such as biology or neurosciences are often ignored, not even to speak of ethics. Developed countries are facing a serious shortage of students choosing to study physics at the end of secondary school, and one may question whether there is not here a causal relation with the way physics is presented to them, although there are many other factors that we know of. On top of this first aspect of training specialists, a new challenge emerged in the last 2 decades. Today, science and technique invade almost every aspect of individual and society life, deeply modify our representations of nature, impact the development of societies, and aim at shaping the future. The whole society is concerned by such a massive transformation, and a good science education for all students on our planet is requested. But implementing such a science for all education faces 2 difficulties. The first one occurs when science has to deal with societal issues, where scientific disciplines are mixed in intrinsically complex and challenging problems, often highly nonlinear. Climate or energy issues are good examples. Contrary to the classical separation of science in disciplines being taught separately, a cooperation, even at an elementary level, between different fields of knowledge is needed to help understanding or solving these complex problems. The probabilistic or statistical aspects are also present, for example, in health issues, vaccination, epidemics, natural or man-related extreme events, earthquakes, nuclear accidents, tsunamis, financial decisions. Here, interdisciplinarity seems the inescapable road education has to explore, education for all. The second difficulty deals with the intrication of objectivity and subjectivity in these issues. Indeed, science may provide or tries to provide objective answers. For example, is global warming real? Is it caused by an increasing carbon dioxide concentration? What is the probability of a nuclear accident? On the other hand, choices made by citizens involve many subjective factors, face alias of all sorts, meet with religious convictions, and are deeply entangled in the person's subjectivity. The good old separation between the object and the subject seems no longer to work. Here, a reconciliation between the person and scientific knowledge seems the road to explore. Hence, science itself is moving further and further in the realm of complexity, making it more difficult to be explored, to be taught, understood, or mastered. Science education has to think itself anew. So, how should we consider teaching advanced science? And in the following, with a few examples, I question how a high-quality scientific training could give to students, secondary to bachelor level maybe, a solid basis to exert a professional life as scientists without remaining blind to the global development of a complex science or to the complex expectations of the society. Namely, to master the tools of a specialized domain in order to use them efficiently, to know and understand the conceptual revolutions, this is epistemology, which have led to modern physics, to stimulate their creativity by avoiding for professors to format them excessively, to open their mind to the borders between disciplines, to the unexpected analogies and metaphors which in the past have often led to great discovery, and that's history of science, to foster a sense of ethical issues, both internal to science, respect of truth and modesty, and external, those are applications of science. Just a few examples. Let's simply observe the slow and timid pace with which the complexity of quantum physics penetrates secondary schools in France, despite 3 Nobel Prizes in our country on the subject, Kastler, Cohen-Tanucci, and Serge Haroche this year. A careful study of French physics textbooks over the last 50 years, done by a colleague in Lausanne, shows a slow, very slow, extremely cautious, and mostly qualitative presentation on the prerequisite that the adequate mathematical language of quantum physics is not by then available to students. A century ago, that's my second example, special relativity had shaken the classical visions of space and time built by human brains on the basis of their concrete experience. Teaching a relativistic world encounters deeply embedded representations which often hamper the student's understanding or creativity. After the thought experiments of Einstein, Victor Weisskopf in the 60s had already addressed this difficulty. I quote here an interesting use of the new tool called Augmented Reality from a recent PhD project developed at Orsay and used for undergraduate students. Pallets or pucks on a carom billiard table are put in motion by a cue and hit, the velocity of light being brought to 1 meter per second. Several frames of reference are available for the spectator who is fully immersed in a 3D dimensional scene, each frame being seen with its own time and relative velocity. Collisions are observed at will from the different frames, while the observer frame with its 6 degrees of freedom is constantly monitored by infrared sensors and computed. In addition to the understanding of kinematics, an haptic cue provides a direct muscular feeling of the dynamical properties encountered in special relativity. This example using augmented reality is far from unique. The power of computers allows to make concrete for students and researchers the modern complexity of scientific domains such as fluid dynamics or plant growth or many others. My second example deals with the compartmentalized manner in which many science introductory courses are commonly taught. Students, I quote, fail to view even physics itself as a coherent knowledge structure. This failure suggests that students would not be able to relate what they study in physics to phenomena encountered in other fields, such as chemistry and biology. This was expressed in a recent paper by a group of Jerusalem physicists and education researchers. Reform in universities are indeed addressing this failure with the goal of motivating students to focus on complex systems without neglecting the necessary core of disciplinary contents. This Jerusalem group proposes an interesting integrated unit on soft matter. Typical topics in soft matter, such as the conformation of polymers in solvents, the cause of bending energy and shapes of membranes, required thermodynamics and chemistry. Despite the complexity of the objects, such study of soft matter with an inquiry pedagogy can focus on everyday materials which are familiar to students and important in materials science and biology. My third and last example deals with language. It represents another communication difficulty introduced by the complexity of modern science. Traditionally, a language made of differential integral calculus and chemical symbols was essentially sufficient to cover most, if not all, science. I mean natural sciences. Today, in physics, electronics with its descriptive tools, chemistry, biology with the genes, quantum mechanics with the Feynman diagrams, the multiplication of symbolic tools create barriers between disciplines. Some introductions of the students to epistemology, including elements of a general theory of language, might bridge this gap and help moving into the expression of abstract concepts. Now I will address this other question, not science for specialists, but science for all students. In my introduction, I have underlined the challenge of a renewed science education preparing all students to deal with complex issues involving science and society, accounting for the complexity of science itself. In the last 2 decades, this theme has been addressed by many reports at various levels, international, such as OECD or UNESCO, regional, such as European Union, the ROCA report, national levels, Royal Society, and many other academies, as well as by the Pontifical academies here in 2007. Without entering here in the richness this detailed analysis provide, I would focus on one point, the concept of big ideas in science. When observing the complex world surrounding them and interacting with it, babies and children ask questions which, in their freshness and spontaneity, represents the early seeds of the whole scientific venture. Later, becoming adults, many will give up this curiosity and decide that science, its language, and its machines, as often presented by the media with sensationalism, are too complex to be understood. They may even enter into relativism, forgetting that science is a search for truth. Or, conversely, discouraged by the complexity, they may entirely rely on the word of experts, renouncing to their prerogatives of free thought. So how can we conceive the goals of science education, say K9 or K12, for modern pupils facing this complexity? Certainly not in terms of knowledge of a large body of facts and theories, but rather as a progression towards key ideas which together enable understanding of events and phenomena which are of relevance to students' lives and later to citizens' lives. This vision of big ideas in science emerged in the 90s and was explored in depth in a recent effort built around the Inter-Academy Panel Science Education Program in parallel with the worldwide development of an inquiry pedagogy in the spirit of La main à la pâte as developed in France after Georges Charpak and Yves Quéré action. I use here the term idea to mean an abstraction that explains observed relationships or properties. A big idea in science is an idea that applies to a wide range of related objects or phenomena, whilst what we might call smaller ideas or small ideas apply to particular observations or experiences. For instance, that worms are well adapted to living in the soil is a small idea. A corresponding big idea is that living things have evolved over very long periods of time to function in certain conditions. Big ideas, with their rich and wide-encompassing power, not only provide explanations of observations and answers to questions that arise in everyday life when facing complexity, but they also enable a prediction capability to deal with previously unobserved phenomena. Big ideas are more abstract than small ones. They require more elaborate cognitive abilities, which are age and intelligence dependent. Science education has therefore to establish adequate progressions from small to big ideas, as, for example, it has been proposed for genetics from grade 5 to 10 by Duncan and co-workers. In this table, I don't give indeed a full list of big ideas. There cannot be more than 10 maybe, otherwise they become excessive, but there cannot be 2 or 3. So one has to find something reasonable in between, which will be the goal of K9 education. And I have listed here this attempt, and there are others of course, like all material in the world is made of very small particles, or our solar system is a very small part of one of millions of galaxies in the universe. I didn't reproduce that one. Or the diversity of organisms, living and extinct, is the result of evolution. But to understand how science seizes complexity, ideas of science are not sufficient, whether they are small or big. Ideas about science must also be conveyed. And one could quote, for example, Science assumes that for every effect, there is one or more causes, some being known, some being unknown. Or scientific explanation, theories, and models are those that best fit the facts known at a particular time. These ideas about science are important because facing the issues which were discussed in this meeting, it's clear that what is more important for all citizens is to understand the process by which science attempts to tell the truth or nature more than knowing a collection of facts. It would be indeed overconfident from myself to suggest that the list of ideas on science or about science are the best ones. But in my view, they simply indicate a direction to go. Science teachers of tomorrow should realize that conveying all the facts and techniques of science will not suffice to prepare future generations. A deeper understanding on the nature of science is needed. So I come to my conclusion. With the triple irruption of complexity in modern natural sciences themselves, in their transmission, and in their interfaces with society, scientists meet a new and difficult responsibility if they wish their activity to remain recognized, respected, and understood. The primary goal of science, namely the search of the truth and the creation of adequate languages to express it, remains indeed unchanged. But a new articulation has to be found between this quest of objectivity and the subjectivity of our contemporaries, whether they are themselves scientists or simple laymen. We had a classical methodology, quantitative, deductive, determinist, and reductionist, which has proven its efficiency. Even when it keeps demonstrating its value in dealing with the complexity of the cosmos, the cell, the history of life, or the climate, it may meet today certain limits. The modern subject becoming himself or herself an object for science and technology resists. I conclude by quoting a very recent editorial published in the French newspaper Le Monde recently, signed by a reputed surgeon under the title Biology and Homoparentality. It's related to the discussion of the homosexuals' position in our society. And I quote, "Experience shows that the speed at which one slides from the forbidden to the tolerated, the allowed, or even the mandatory essentially depends on the rhythm of scientific discoveries, no matter what the ethical issues are." It seems to me that the question of the complex interaction between modern science and the person dealt with education cannot be expressed in a better way. Thank you.